So let's proceed with our next topic, topic 4 on logic gates and Boolean algebra part 1. So this is the overview of the content for this week's lecture. So we're going to go through basically this week for logic gates. We're going to go through logic gates, and we're going to cover basically what we need to know is we're going to cover the basic AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR, and also XNOR gates. And for each gate, we need to know what is the logic symbols, what is the Boolean equations, what is the truth table, and also what is actually a timing diagram. And also we're going to be looking at briefly what it means by propagation delays in logic gates, some examples of digital ICs, and also for this week we're going to cover one subtopic in Boolean algebra, which is the single variable theorems. Specifically, we're going to look at the annulment, identity, idempotency, complements, and involution. Okay, so what is logic gates basically? So logic gates is a primitive or a fundamental building blocks for all digital circuits, where a logic gate has at least one input and only one output. So the key thing here is only one output, but it can have more than one inputs. The output actually depends on the function of the gate and the combination of all the inputs. So depending on the function here, FAB, the function f here is in fact depends on the particular function of the primitive or the building block. So for each gate, we need to know what is the graphical symbol. And what is a mathematical expression or the Boolean algebra for the logic gate, and the truth table, the canonical truth table, which contains all the input combinations and what are the outputs, the timing diagram, which shows the input-output behavior graphically. So let's look at the first gate here, the AND gate, the most basic one. Basically, in the AND gate, we have a high output only if all the inputs are high. Described by the following Boolean equation here as follows: f equals to ab. So also f, we can also see that the AND gate can also be represented by a dot b. A and b here is typically used in programming, and then also a and b in set theory. But typically in Boolean algebra we use f equals to ab, and here is the symbol. So a timing diagram shows the relationship between the input and output. So for example, here if we have the input A and B, these are called the inputs, and we have an output F, which is one output F, and here is time. Okay, on the x-axis we have the time, on the y-axis we have the inputs and the outputs. So here is your inputs A and B, and here is your output, which is F is equals to A dot B. So at this particular time, during this particular time, we see that A is actually equals to 0, and here is also B equals to 0, and we know that for an AND gate, we have the description here is that the output is high only if all inputs are high, else it will be 0. So is all of the inputs high during this? No. Therefore, the output here becomes 0. So similarly here during this time, we have A equals to 1, B equals to 0. Are all the inputs high? No. Therefore, your output during this time is actually 0. So you can do the same, and here we can see that at this moment in time, we see that A is equals to 1, B is also equals to 1, and therefore we have our F output of the logic gate equals to 1 only at this time. So let's look at the OR gate. So given the truth table here, you can also derive the truth table for the AND gate for you to try yourself. What should be the truth table for an AND gate? But here we are looking at the truth table for an OR gate. So for example, if we put 0, 0 on AB, 0, 0 on AB, we know that the output is going to be 0. Okay, we says here that for an OR gate, we have a high output if any of the input is high. So here we have a 1 here on the B, therefore one of the input is high. So for our OR gate, we have 0, 1, and output F is equals to 1. AB, so A equals to 1, so one of the input is high, therefore your output F is equals to 1, and 1, 1 also gives a 1. Okay, so for example here, at the given time, if I give a 1, 0, we are going to get 1 here, according to the truth table. So for an OR gate, we can represent using the following Boolean equation, which is A plus B. Okay, be careful that this is not a regular plus, this is an OR Boolean expression, the plus. So for example, if you have 1 or 1, the result is 1 and it's not 2. Okay, so we can also represent the OR gate using the A bar B, A with a bar, like so. This one typically used in programming. We have A bar and a B, and in the set theory we can do something like this, A VB. Let's have a look at the NOT gate. So a NOT gate actually inverts its input. NOT gate is also known as an inverter. So inverter or NOT gate basically the same thing. And this is a truth table of the NOT gate, where if the input is 0, we have the output 1. If the input is 1, we have the output 0. So for example here, if I put 0 in the logic 0 in the input, we are going to get logic 1 in the output. And a NOT gate is represented by the following Boolean equation, where we have simply a bar on top of the input. And the NOT gate can also be represented F equals to A T. Also F is tilde A. So in programming, normally we use tilde A, and we can also use AT as an invert. Okay, so we can also have logic gates with more than 2 inputs. So just now we saw an inverter or a NOT gate with only 1 input, the OR and the AND with a 2 input. Now here is a 3 input AND. So here is a 3 input AND gate. So what is the characteristics, or how does it behave when you give a certain input values to the 3 input AND gate? So here is your truth table, and we can see that the output is 0 all the time, except when we give A, B, C equals to 1, 1, 1. So the only time that the F is equals to 1 if we have 1, 1, 1 on the input. Otherwise 0 all the way until 6 here, decimal 6, we are going to get F is equals to 0. So for the OR gate, the output is true when any input is true. So we can also derive the same way, that for the OR gate, the output is 1 when any of the input is 1. So in other words, you have a 0 only during this case for a OR gate. Okay, here is for an OR gate, you have 0, 3 OR, 3 input OR. So for a 3 input OR, for example, we have a 0 only in the case when all of them 0, else all of it is going to be 1. Any of the input is true. So for the NOT gate, we cannot have more than 1 input. So for a NOT gate, there's always going to be only 1 input is allowed. So gates can also be connected to make a logic network, some arbitrary or some any logic networks that we want. And output can be connected to more than 1 input. So for example here, we have in this case, we have only 1 output of gate 1. This is gate 1 connected to 1 input of gate 3, and here gate number 2 is also connected to the input of gate 3, but in fact we can also connect this to another gate. So basically it's saying that the output can be connected to more than 1 inputs or different gates. Inputs can be connected to only 1 output. So an input can only be connected to 1 output. So for example, this input is only connected to this particular output. Okay, so this input is connected to this output. This input also connected to only 1 output. Most common is the NOR network. So this is an example of the NOR network. So here we can see it's a AND, A and B, C and D, A B plus C D, or A and B or C and D. So this is also called the NOR network. So network F A B plus C D is shown below. So let's look at another type of logic gate, which is quite important nowadays. A lot of people, complex chips, sometimes they only use NAND gate because it is very efficient in VLSI circuits, in chip design. NAND gates is very efficient. due to its structure, okay, due to its semiconductor structure. So let's see how the NAND gate functions. So a NAND gate, basically the Boolean expression is FA dot B with a bar. So basically we can think of it is a AND gate with a NOT at the end. Okay, so this is also, you can say, is sort of like a NAND gate function, where if you look at the truth table, the output is 0 if and only if A and B are both 1. Okay, output is low when all inputs are high, and then the output is high otherwise. So this is the only time that the output is 0. So as you can see here, this is an equivalent NAND gate. Another important logic gate is the NOR gate. So in the NOR gate, we have a basic OR with a bar at the end there. Okay, so similarly, we can have something like this, where we have an OR gate connected directly, to an inverter. And let's have a look at the truth table. So in the truth table, we know how the OR functions. So if you remember the OR function, in the OR function we have 0, 1, 1, 1, and we can see that this is for the NOR. So in the NOR function, basically it's an invert of the basic OR function. Okay, and let's have a look at another important gate. Okay, besides the NAND and the NOR, the XOR is also very, very important and widely used. This is the symbol, so it looks like an OR gate, except that we have another kind of a curved bar there. Okay, and that is a symbol for an XOR gate. Okay, it's an XOR gate. So let's have a look at the truth table of an XOR. So an XOR output is high if one and only one input is high. Okay, so we can see here that if it's 0, 0, then the output is 0. If it's 1, 1, the output is also 0. So if either one of the input is high, then only that we have a logic 1 on the output. And here is the symbol for an XOR. We have a plus with a round or a circle there. And this XOR can also be expanded into a Boolean equation, which is simply equals to A bar B plus A B bar. Okay, so this function is actually our XOR function. And finally, okay, this should be our last basic gates that we're going to look at, is the XNOR. So in the XNOR gate, what we have is basically the invert of the XOR. So this is your XNOR, and the XOR is just going to be 0, 1, 1, 0. So remember, in the XOR, if one of them is a 1, we have a 1 on the output. If both are the same, so these are the same 0, these are also the same 0. And in XNOR is the invert, where we have the inverter at the end of the XOR, and therefore a 0 becomes 1, a 1 becomes 0, a 1 becomes 0, and a 0 becomes 1. Okay, so basically you can say here that the output is high when both inputs are equal. So if both are equal, so for example, if I put 1, 1, okay, then the output of the XNOR will be 1. So output is high when both inputs are equal. Okay, similarly, if I put 0, 0, okay, the output is also going to be 1. Okay, and here is the symbol, the Boolean expression, the Boolean expression, which is A plus circle, and then we have the bar on the top. And it can also be represented by this Boolean expression, A bar dot B bar plus A dot B. So for example, okay, so for example here, if we say that A is equals to 0 and B is equals to 1, okay, 0, 1 is here, and we know that the XOR is going to be 0. So here we can see that 0 bar dot B is 1, so 1 bar plus 0 dot 1. Okay, so here is going to be 1 dot 0 plus 0 dot 1. Okay, so let's continue up here. So 1 dot 0 is 0 plus 0 is equals to 0. So we prove through there that the function of XNOR can be represented by this Boolean equation. Let's look at the basic propagation delay. So in logic gates, when we apply input, okay, there is a delay at the output after applying the input. So for example, if I apply, if I'm currently at 0, I'm currently at 0, and here we're going to get a 1, and now at one particular moment, okay, so during this moment here, I'm going to give a 1 on the input. So it's going to rise up, so I'm going to give a 1 here, and what is going to happen to the output as soon as I give a 1 or I increase, okay, the voltage value on the input. So as I increase the voltage value, I'm going to get a 0 on the output, and as you can see here that the output doesn't switch at the exact time that we switch on the input, but there is a certain delay called the TPHL, or the high to low propagation delay. Okay, the high to low propagation delay. So this is so there's a certain delay until we see a 0, okay, a 0 on the output. Okay, and that is called the high to low propagation delay. Now what about the low to high propagation delay? So looking at the low to high propagation delay, if I put a 1 here and 0, so for example I have a 1 here on the input, and obviously we're going to get a 0 on the output of the inverter. And now if I give a 0 at this moment, okay, when are we going to get a 1 on the output? Okay, and apparently it doesn't happen instantaneously, okay, so it doesn't switch at that moment, and it requires a certain time or a certain delay because there is some physical, is a transistors inside here, transistors delay. So the reason for the delay is basically due to the transistors delay inside the logic gates, because physically inside there are some transistors. So with that, we have a certain low to high propagation delay from the input to the output. Let's look at the example here. Write the Boolean equation for the following logic circuit. So what is the method here? So the method is, we are going to look here, this is an AND gate. Okay, we know this is the AND gate, and we know that in Boolean expression for an AND gate we have A dot B. So here is A, B, okay, so like this. And the second AND gate here is going to be, this is a B invert, B bar, and here is a C invert, and therefore here is going to be B invert, C invert, like this. And the last gate here is going to be C, so this is not C invert. Here we see that it's a C, and here is actually a A, okay, and therefore here is actually AC. So therefore our F here is in fact is AB plus, this is an OR gate, so it's going to be OR plus B bar C bar plus AC. Okay, so this is our Boolean expression at the end of the logic network. So if we apply 001, so if we apply 001, okay, so this is our A, B, C. So A is 0, B is 0, and C equals to 1. So what is going to be the output F? So there's two ways to analyze this. Let's look at the first one. The first one, we look at the output of every logic gate. So for example, if I put A, B, 0, so here we know that if I put 0, 0 here, we're going to get 0. If I put 0 here, we're going to get 1. I'm going to get here is 0. 1 and 0 is going to be 0. Here is going to be 1, and here is going to be 0. I'm going to get the 0 here. 0 or with 0 or with 0, we are going to get F is equals to 0 in here. So another way is to look directly at this Boolean equation or the Boolean expression, and we see that here is going to be 0 because A dot B, okay, so A is 0, B is 0, C equals to 1. So A dot B is going to be 0, okay. B bar dot C bar, so B bar dot C bar is going to be 1 dot 0, okay, and then AC is going to be 0 because 0 and 1 is going to be 0, and therefore we can see here there is 0 or 0 is going to be 0 on the output. Okay, so just a briefly overview of the digital IC. So digital IC is a collection of gates on a single chip of silicon. So inside here we have logic gates. Okay, made from transistors. Okay, so logic gates are typically made from transistors. So inside here all we have logic gates. It's just a package that is different. So you can actually buy in the DIY electronic shops a DIP type, the SOIC type, or the PLCC type logic gate. So for example, here might be the VDD connection, and here might be the input 1, input 2, and so on. Okay, so for example here, this is a 14-bit example of some of the digital ICs that you can find in an electronic shop for DIY. So for example, here is a NAND gate chip. So looking at the notch here, so pin number 1 is actually the left. Okay, so pin number 1 is on the left. So pin number 1, number 2 here is both are inputs. Okay, so you can see that both here pin number 1 inputs. Number 3 here is the output. Okay, number 3 is the output of this particular NAND gate. Okay, here is a NAND gate. So 4 and 5 is also the input of this NAND gate. 6 is the output of the NAND gate. 7 you need to connect to the ground to give the ground, and VCC here is to supply power to the logic gates. 12 and 13. Okay, so the pin count is left notch and then going down 1 to 7, and then it goes 8 here on the right, and then all the way to the top to 14. Okay, so similarly here we have 1 all the way 7, 8, and up. Okay, and here example of a deep DIP package of the logic gates that you can buy from the shop. So for the inverter, for example, pin 1 is your input to this particular inverter, and pin 2 is the output of the inverter. So let's say you are implementing or designing some logic functions and you need an inverter, you need a NAND gate. You can simply buy these chips, and you can construct, you can buy a breadboard, a circuit board, and you can actually construct your own circuit to perform whatever function that you want to perform. Okay, and similarly down here we have an AND gate. Okay, here is the AND gate chip, and here is your OR gate chip. And you can also have some other complex chips as well. So this is the most basic one, but then you can also have a chip, okay, IC chip with 1 billion gates. Okay, so here is 4 gates. Okay, here is 4 gates. So you can actually have a chip that contains 1 billion gates, and that is called Intel chips. Okay, or AMD chips. They contain 1 billion logic gates inside one package IC. So the basic one, you can have 4 gates. So let's look at some of the terminology here. So when we talk about the logic gates, if you have a chip, okay, transistors per chip. So if you have a chip, so basically you can say that the inverter, okay, or the NOT gate, 2 transistors. Okay, two transistors for inverter. A NAND contains 4 transistors. Okay, so inverter 2 transistors, a NAND gate 4 transistors, and if you have a chip with less than 10 gates, okay, so probably here, if you have less than 100 transistors, then they call it the small scale integrated circuits. If you have a chip with 10 to 100 logic gates, for example flip-flops and registers, we're going to look more into detail later on, those are called the medium scale integrated circuits. And if you have 100 to 1000 logic gates inside the package chip, is typically a memory or a macro. And then if you have more than 1000 logic gates or 1 billion gates, those are normally typically can be a microprocessor or a system on chip, and those are called the VLSI design or the VLSI chips, the large chips. So for example, your Intel CPUs are considered as VLSI chip. Okay, so let's proceed here quickly. For this week, we're going to cover a little bit on the basic Boolean algebra, on the single variable theorems. So we're going to look at 1, 2, 3, 4, 5 here. Okay, so let's look at each one. So in the annulment theorem is that if you have a input, okay, which could be, so A can be logic is a binary, so it's logic 0 or logic 1. And if A and with 0, we are going to get 0. If A plus or A or 1, we're going to get 1. In the identity A dot 1 equals to A plus 0 equals to A, idempotency A dot A equals to A plus A equals to A, complements A dot A bar equals to 0, A plus A bar equals to 1, and we have the involution. If we do a double invert, A double invert equals to the original A. Let's look at a little bit more detail here. So for example here, if we constant, so if we supply constant ground, okay, if we supply constant ground on one of the pins of the NAND gate, okay, and here is input, okay, here is your input A, which can take a value of 1 or 0, but then if this is tied to ground, then automatically your output will be 0. Okay, so you don't need to look at the A. We know that regardless of the value of A, if you end it with 0, we are obviously going to get 0 by looking at the truth table of the NAND gate here. So you can see that A here, okay, B here is 0, fixed at 0, and automatically your F will be 0. Now for the OR gate, if we supply a constant 1, and here is your input, then automatically your output will be 1 regardless of the value of A. So even if A is 0 or A is 1, if we see that in the truth table of the OR gate, that if the B is a constant 1, therefore your output will be 1 regardless of if you put 0 or 1 on the value of A here. So this is called the annulment theory. In the identity theory, okay, in the identity theory is now the output is going to follow the input. Okay, so that is the key idea in the identity theory, that if you want to get back the A, we give a 1 value. Okay, so we give a 1 value, so we can see here that if we put a constant 1, okay, if we put a constant 1 on one of the inputs, then the output is going to follow the other input. Okay, it's going to follow the other input A. And for the OR gate, in order to get the A value here, then we need to supply a 0 or a ground. Okay, so if we supply a constant ground on the B, we are going to get, you can see here, A transferred to F, and A here also transferred to F here. So the third one is idempotency. So in the idempotency is we are going to get the same value. Okay, the same value. So for example, if I put a 1 here, therefore this is going to be 1 1. So 1 and 1 is going to be 1. Okay, and similarly, if I put a 0, here, it's going to be 0 and 0 0. Okay, so in the NAND gate idempotency theorem, A dot A is equals to A, and then for the OR gate, is the same. So if I put a 1 here, 1 1, you're going to get a 1. Okay, if I give a 1 on the A, both inputs going to be 1, so 1 1 A. Okay, and similarly, if I put a 0 on the A, we're going to get a 0. So meaning that whatever the value of A, if it's a 0, we get a 0 in the output. Okay, if A is 1, we're going to get a 1 in the output. Okay, so this is the third one. The number 4 is the complements theorem. So in the complements theorem for the NAND gate, okay, we can see that A dot A bar. Okay, so here is A bar now. So A dot A bar is automatically going to be 0. Okay, regardless of the value A. So it doesn't matter that if A is 1 or if A is 0. Okay, if we put A and A bar on the input of an NAND gate, we are going to get a 0 on the output. And similarly for the OR gate, if we supply A and A bar on the input, okay, on the input of the OR gate, we are automatically going to get 1 regardless of the value of A. Okay, so if A is 0, it's going to get a 1. If A is 1, we are still going to get a 1. Okay, so let's have a quick example here. I'm putting my A is 1. Here is going to be 1, 0, 1, or 0 is going to be 1. Okay, and similarly, if I put a 0, 0, here is 1, 1. So regardless of the value of A, we are still going to get a 1, and this is called the complement theorem. And finally, we look at the last theorem here. It's called the involution theorem, whereby if we put the two inverters back to back in series, okay, so here is the series inverter, we are going to get back our original A. So for example, if I put A here is 1, I'm going to get a 0 here, and here I'm going to get a 1 here. So basically, I'm going to get back here. Okay. Similarly, if I put a 0 in the beginning, similarly, if I put a 0 here, I'm going to get a 1 here, I'm going to get a 0 here. Okay, so you can see that this is also known as a buffer. Okay, a series inverter or a buffer, where we get the same A. Okay, we get the same A back to the front. So there is some application for a buffer that we'll probably see later on in your studies. There is a purpose to do the buffering. So based on the truth table there, okay, involution theorem says that if you give a double inverter in series, okay, which performs a buffer function, we get back our original A. Okay, so that's it for our lectures topic for this week, and we'll cover more on the Boolean algebra in our next